concept with these two graphs that you need to understand, and that's delta H. And that is the heat of formation or change in enthalpy. And it's a little bit confusing to understand why it's negative negative in exothermic and positive in endothermic. The mathematical explanation is the formula for the change in enthalpy, labeled delta H, is equal to products minus reactants. And if your products are lower than your reactants, let's just give them an arbitrary value of 10 versus 30 over here. Well, if you're going to be subtracting 10 minus 30, you're going to get a negative number. And so that's why your delta H is negative in an exothermic. So if you'd like to remember that, you can, but it's very easy, or easier for me to understand these things intuitively rather than simply just memorizing these facts. So a negative delta H, in summary, is an example of an exothermic reaction where you're going to be the system is going to be losing this energy, but the surroundings are going to be gaining it. You're going to be releasing that energy in the form of heat, in any form of energy. While on the endothermic side, you're going to be subtracting a big number, or sorry, a small number from a big number. And this delta H, again giving these values of, let's say, 10 and 30, same ones. Well, 30 minus 10, excuse me, is equal to 20. So your delta H is positive here. So those are important things to understand. Finally, let us label, move this aside. I'd like to look at that again, just rewatch the previous segment. Let us label a full diagram. So this diagram is going to be an exothermic diagram. So you're going to begin up, you're going to have some kind of dip, and it's going to fall and then going to stabilize. So oftentimes they'll draw arrows, and it's confusing for students, but really it's just pretty simple here, because it's just asking for the from the 0 to the top, which is just the value here. Reactants and products. So I'm going to draw a bunch of lines, and then we're going to figure out what they mean. I believe those are all the ones you need to know. So this is the value for, and here you'll have energy, label the rest of the graph, energy in joules, and this is time elapsed, but it really doesn't matter because you're just looking at the end result versus the beginning. So it doesn't actually matter how much time. There's no real computational or no real numbers here. So again, this is just this arrow is a representative of products, and this arrow is a representative of reactants. So what are these other things? Well, before we we figured out that to calculate delta H, or the change in enthalpy, is the difference between the products and the reactants. Well, if we take the difference between here depicting the products and the reactants, well, you're actually left with this space. And that space is your delta H. So your delta H is always the line drawn from the reactants to the products. We talked about this before. That line over here is the activation energy. And that's the energy you need to put into the system in order for it to move. And finally, this whole line is the activated complex. Another important thing to understand with these reactions is they're reversible, which means that if I take this chart and I invert it or mirror it, and I'm going to be starting with the products, moving to the reactants, it's going to be an endothermic, because notice how the products are now lower than the reactants. So